Guys, this is Shelby with the Rogers Public Library. So this week I want to talk to you guys about surface tension. And to do that, we're going to need to talk about water, and we're also going to need to talk about how the way that molecules are shaped affects their behavior. So to start off, when we talk about surface tension, we're talking about liquids. So what we know about liquid is it flows, right? If you move the container it's in around, it'll move with that. We also know that it'll fit into a container, right? And when it fits into a container, it forms a surface. Now, anytime you have a surface of a liquid, you're going to have something called surface tension, and that's like a kind of a force. You can think of it almost like a skin. There's a certain amount of energy that you need to be able to break the surface tension and get in there. And we can do a really cool demonstration of that using a needle, right? So this is steel, it's more dense than water. And we just drop it in, it falls to the bottom. And that's because the needle is breaking the surface tension. It's accelerating due to gravity and it breaks the surface tension. But if we set it down very gently, I can pull this off. This is kind of tricky, but there we go. So finally, we got the needle to float in the water. So this is happening is because even though the needle is denser than water, it's not the force that the needle exerts on the surface of the water isn't enough to break the surface tension. But we can change that, and all we need is a little drop of dishwashing soap. We dip it in here, and ta-da, it falls. So to understand why this happens, we're going to talk a little bit about water, right? So this is what a water molecule looks like. It's a little V shape, right? And it has one oxygen atom and two hydrogen atoms. And the important thing to note about water is that it's not symmetrical, right? So it has positive charges on the hydrogen side and a negative charge over here with the oxygen. And because that, it acts like a little magnet. And water molecules will bind to each other very strongly, right? But we don't say that the water is a magnet. We'll say that it has dipoles, right? So that just means it has two poles, positive and a negative end. And specifically, because this has hydrogen atoms in it, we say that it forms hydrogen bonds. That's what this, and hydrogen bonds are an example of intermolecular forces, right? So there's the energies that bond different atoms together into one molecule. And there's also the energies that bond different molecules together, and those are intermolecular forces. And dipoles aren't the only forces that there are. When we have dipole bonds, we say that we're talking about polar molecules, right? But there are some molecules that are nonpolar. And so this is an example. We actually talked about this molecule on a couple weeks back. This is carbon dioxide, right? So it has a carbon atom and two oxygen atoms. And what you'll notice about this one is, unlike this guy, the ends are the same, right? And so it doesn't have different charges on the different atoms, and it doesn't work like a magnet. But there is a little bit of attraction between carbon dioxide molecules. Those attractive forces are called London dispersion forces. So they're a little bit different. And one cool thing to note is that when we have strong bonds between water molecules, we get a liquid. And when we have weak bonds between carbon dioxide molecules, we get a gas. Now, there are some nonpolar molecules that are liquids, right? And you know one pretty well. This is cooking oil, right? So, you use this to cook fries and chicken nuggets and stuff like that. And this is what the molecule looks like. So it's really big. It doesn't matter what these lines are and what the groups are over here. What matters is its shape, right? So we have a very symmetrical molecule. All the charges are kind of evenly distributed here, and they're evenly distributed here as well. And because of that, it's nonpolar. Now, the difference between this molecule and this molecule is this one's a lot bigger. And when molecules are really big, the attractive forces between them are greater. And so we can end up with a nonpolar molecule that's a liquid like this, as opposed to one that's a gas. And there are even some nonpolar molecules that are solid, like coconut oil or butter, right? Those are both oils that are solid at room temperature rather than being liquids. Okay, Let's see. Look at my notes. Right. Great. Okay, so now one important thing to note about the polar and non-polar molecules is that they don't mix together really well. So I'm going to show you guys this with these two plates. So this one has this oil, I painted it on with a brush, and this one's just a clean plate. Now the molecules in ceramic are generally speaking polar. And so when we put water on it, the water drop flattens out and it kind of forms little puddles and stuff, right? But when we put it on this plate, we get droplets, right? One way to think about this, about the different droplets that water forms, is that it's making minimal surfaces, right? Kind of just like we talked about with soap bubbles, right? It's forming circular shapes because that prevents the molecules from that allows the water molecules that are really attracted to each other to be close and far away from the oil molecules that they're not attracted to very much at all. Now, the next step is, how do we connect these polar and non-polar molecules with surface tension and with our dishwashing detergent? Well, we can do something cool here. We can put a little bit of detergent into this water. Now let's see if it acts the same way. No, look, see, it spreads out, right? And if we put a drop here, this one spreads out too, rather than forming surfaces. So what soap is it's amphiphilic, and that means that it has one end that is nonpolar, kind of like this, right? This end over here, oh, this is the right way. This end over here looks a lot like this end over here. But on this side, we have little plus and minus signs, just like we have with the water molecule. So that allows water and oil to mix together, and for the water on the plate to mix in with the oil on the plate. And how this affects surface tension is actually pretty cool. So when you don't have an oil or anything, when you just have pure water and you add soap to it, what happens is that the polar end will bond with the water, and the non-polar end will face upwards, right? It's facing towards the air so that it minimizes the contact with the polar water molecules. When that happens, instead of having a surface made out of water, you have a surface made out of non-polar soap molecules. And because they're nonpolar, the intermolecular forces between them are weaker, and so it takes less energy to break the surface, and the needle falls. Yeah. So that's our experiments. And in just a second, we're going to get to the craft. So for this craft, it requires a little bit of setup. So what you're going to need is you're going to need a pan. It doesn't have to be an aluminum one like this, but this is just it's easy to clean, so we're using it. You'll also need some paints. I'm using acrylic, and you'll want to water them down. And then you'll need liquid starch. You don't actually have to use liquid starch for this. So what we're doing is called paper marbling. And you're going to want to create what's called a size, and liquid starch makes a good size. But if you don't have this or you don't want to use it, you can also mix cornstarch with water, 2 teaspoons for every cup, and cook it for a little bit until it starts thickening up. And you can use that as a size instead. Now, we're not doing that today because it takes some prep time. You have to cook it, and you'll need a grown-up to help you with that. And then you have to let it cool down. But this, it's ready to use right out of the bottle. So when I did this before, I think I ended up using about 3 cups of liquid for the size. It doesn't matter exactly. You just want it to be able to cover the bottom. Right? So what we're going to be doing is we have the size, right? And we can think of the size kind of like a canvas, right? We're going to be painting on it using our watered down paints. So we have some pipettes. Again, these are just something that makes it a little bit easier because you're going to want to drip the paint on here, right? You're trying to make the paint float on the surface without breaking the surface tension, just like the needle. And you can do this other ways, like if you have a spoon or if you have a brush and you want to sprinkle it on. Let's see. So we're going to get some drops of paint over here. You can see it spreading out and forming cool circles. And these are actually called Bernard Marangoni cells, and they form when you have differences in surface tensions. So we have some different paint spread out, and we're going to take a comb. I just made this with toothpicks and hot glue. You can, or as well as some cross sticks. You can also use duct tape instead of hot glue. Now we're gonna mix it together, right? This is the actual marbling part. So we're forming cool patterns. And now we're gonna take the paper, and we're gonna set it down in the water. And this is just plain copier paper. It works perfectly fine with this. And we get a really cool pattern, right? So I'm gonna set it down. And you can actually, so you can put a second piece of paper down and it'll absorb a little bit more of the paint and it'll form a different pattern. It's a lot fainter. This is actually, it's an example of mono printing, right? So it's really cool in that you can try as much as you want to try to make the same pattern twice, but just by the nature of the way that the paint interacts with the water it's not ever going to be exactly the same. So you end up with unique mono prints that you can only make once. The other cool thing about this is that you while it does take a little bit to set up, is you can end up making a lot of artwork this way. The size, or with just a little bit of paint and a little bit of liquid starch, you can make a lot of these prints. Now, one thing to note is that the liquid starch is kind of sticky. So once you get it to this stage, you are going to want to let it dry for a little bit, right? So that the paint can set in, and then try to wipe them down with like a damp cloth, or you can even put it under this faucet in the sink. It sounds silly, but as long as it's not running super fast, you can rinse some of the liquid starch off without upsetting the paint, and it'll dry a little bit better. And here's what some of my finished artwork looks like. So they're kind of faded, right? I rinsed some of these off, but not all of them. Here are some of the ones that I didn't rinse off, and you can tell they're more vibrant, but they're all unique. And then there are some colors that you might not want to use. If I did these again, I probably would not have used the brown color. I was trying to do some fall color patterning. But then as far as, once you make the prints, and if you decide to wipe them off, the next step you'll want to do is make them flatten out, right? You can tell some of these are curled. And the way that you make them flatten out is either when they're almost but not quite all the way dry, or when they're already dry, or if they're already dry and you put a little bit of water on them just to moisten them slightly, then you can put them between pieces of cardboard and put like a book or something on top of that, and it'll help them flatten kind of straight instead of being curly. Yeah, so that's our craft for this week. I hope you guys liked it. I'll see you next Thursday.